Yay! It's working. It's working. We're recording. Anyone want to say anything? Hey, said Rodifer. Rodifer says, hey. It's I Love to Write Day. Hey, yeah, I Love to Write Day. Fake it till you make it, right? What's that? Hey, what's the best way to become a better writer? Wrong. To read. The best way to be a better writer is to read more. Yeah. Now, it depends on what you read. You don't want to read like C-spot, run. C-spot, run fast. That's not going to improve your writing. But if you read like Faulkner or Hemingway, I don't know. He had a very simplistic writing style, didn't he? Yeah. The Old Man and the Sea is just like one super long fishing trip. But you know what? He makes it drudgery because that's what the guy was feeling. You kind of experience the drudgery of just sitting in a boat for hours on end, waiting for one fish. So, a good literary device. Yeah. Anyway, and if you ever read Finnegan's Wake by James Joyce, that guy's pretty complex. You never really finish that book because as soon as you get to the end, it wraps around, you go back to the beginning. So, you got to have a friend who's willing to jump in and save you. All right, cool. We're recording. That's the thing. And it's I Love to Write Day. Did you just dab? Oh, dang it. We're not getting started yet. All kinds of interruptions. Hello, this is Corpy. Oh, I think you got the wrong number. This is a classroom. Have a good day. He was looking for some person named Debbie. I think it was a tax collector or a debt collector. Yeah. All right, so e to the x. Is e to the x going to be growth or decay? Growth. Should we start the recording over, or should we just leave all of those stuff on the front side? Leave it. Okay, good. It is growth, so something like that. I'm not going to be like taking out any kind of measuring device to see how steep you're making it. That could really be the graph that you draw for any exponential growth function. 2 to the x, e to the x, 100 to the x, it doesn't really matter. There is a horizontal asymptote on the x-axis. That only affects the left-hand behavior. And what is the y-intercept? Yeah, 1. So you can label that as 0, 1. Now, this then could be the graph for any function of the type a times b to the x. Of course, b could be any real number as long as it's the correct real numbers. And for growth, remember, b just has to be greater than 1. So any real number greater than 1, this could be the graph. What happens if b is between 0 and 1? It's decay. Yeah, good. All right, so once we have the graph, we'll call that one f of x equals e to the x. No, here we go. I love to write. Let's answer the question. The domain, we'll call that big D subscript f, colon. What is the domain? All real numbers, so you write like that. Is that going to change for any exponential function? Nope, that's an easy question. The range, R sub f. What's the range? 0 to infinity. I like that. I'll write it in like that. Of course, infinity always gets a what? A bracket or a wimpy parenthesis? Infinity? Can you ever get to infinity? You can try, but you'll always fail. So infinity or negative infinity, remember, always get a parenthesis. Now the question is, do we include 0 or not include 0? There's a horizontal asymptote. We'll never reach 0. So you can write it in interval notation, or you could say it's the set of all y's such that y is strictly greater than 0. That would be the set builder notation. Remember, the range then is important in respect to the horizontal asymptote. In this case, it lives above the horizontal asymptote. Sometimes it could live below the horizontal asymptote, as you'll see in the next few examples. That makes a good test type question right there. On a multiple choice, just asking you for the range of a function, giving you the equation. And I'll show you how to do that here in the next two examples. But we're not done with this one yet. So intercepts. We have two types of intercepts, right? We have a y-intercept, and we have an x-intercept. The y-intercept is generally the easier of the two to find, because all you have to do is plug in a 0 for x, and of course we already know that's 1. And that'll be true for all exponential functions of the form a times b to the x, whether they're growth or decay. What's the x-intercept? There are none, so just put none, right? It never crosses or touches the x-axis. How about intervals of increasing or decreasing? You have to answer that question by looking from left to right. Is this function going uphill or downhill? Uphill. So we'll say it's what? Increasing. Now, where is it increasing? For all reals. Yeah, and we're listing it as an x interval. So if something is increasing or decreasing on an interval and doing nothing but, you could say one of two things. You could say it's monotonic or strictly increasing, in this case, over its domain. You can answer it that way. There's a couple ways to answer it. Over its domain, which, of course, we've already answered to be all real numbers. You could say it's strictly increasing for all real numbers. You could answer it like that. Or you could say it's strictly increasing from, let's do this. Let's put x epsilon. I like that. What does that mean? X is an element of, or x is inside the interval from negative infinity to infinity. Because that kind of reinforces that we are talking about x values. We're looking for the values of x where the graph is going uphill. In this case, it is uphill everywhere. Let's talk about one other thing here that I don't think we mentioned too much of. It's called one-to-oneness. You can do it like that, or you can actually write it out if you love to write, like I do, one-to-one. What do you think it means to be one-to-one? Anyone here in a one-to-one relationship with somebody? Do you think that means that one of y'all is two-timing the other person? Oh, y'all don't want to answer that one, do you? Okay. That's how rumors get started, I guess. To be a function, remember, it has to pass the vertical line test, which means that every x has only one y value, or no more than one y value associated with it. But think of x squared. It passes the vertical line test, but x squared, like if you look at the y value of 4, 4 can come from a negative 2 or a positive 2, right? So that 4 would be two-timing the x value, so that would not be one-to-one. So in order to be one-to-one, every x can have only one y value, but also every y value can only come from one x value. So not just passing the vertical line test, it would also have to pass the horizontal line test, and x squared does not. Does this graph pass the horizontal line test? Yes, it does. For every x, there's only one y, and for every y, there's only one x. That's kind of romantic, right? One-to-one, like Minnie and Mickey Mouse. Hey, I think Mickey Mouse Day is tomorrow. But today is I Love to Write Day. Let's write that down. One-to-one or one-to-one? Yes. Since, we can write it out, since f of x passes the horizontal line test. That could be a note to yourself. The horizontal line test. Not all functions pass the horizontal line test. The ones that do are very, very important because they have what's called an inverse. And they're very useful then for coding and decoding. There's only one way to code a message and only one way to decode it. We say that they're invertible. But right now, it's just one-to-one. Okay, cool. End behavior. So we already talked about how we would describe that with the right limits. The limit as x goes to infinity of f of x. That would give us the what end behavior? Left or right? The infinity gives you the right end behavior. And the negative infinity gives you the left end behavior. Make sure you're putting your f of x in there. All right, what is the right end behavior? You can either look at the graph, what's happening as you go out on the graph to the right. You're going up to infinity, or dne, right? But which is the better answer here? Infinity or dne? Infinity, because it tells you why it doesn't exist. It doesn't exist because it's increasing without bound. And then on the bottom here, the left end behavior, if you look at the graph, it goes out to the left. It approaches 0. Now remember the definition of a horizontal asymptote? If either one of the two end behaviors equals a finite number, and the bottom one does, so f has a what? Horizontal asymptote. Good, at y equals 0. So that's a very important feature of exponential functions is the horizontal asymptote. But they only affect the graph on one particular end. Now, if you didn't know what the graph looks like, is there a way to figure out the end behaviors by direct substitution? Kind of. You can't really plug in infinity per se, but let's kind of take some exploratory liberties here. If you plug in infinity, what is e to the infinite power? It's big, right? We'll call it huge, big. Or big, huge, big, huge, huge, big. Let's do it like Trump would say it. big, huge, right? Because he doesn't pronounce the H's. Big, huge, which is another name for infinity, right? And what if you plugged in a negative infinity? You would get e to the negative infinity, which is the same as 1 over e to the what? Positive infinity. So what happens to a ratio when the denominator gets big, huge, and the top stays a 1? Yeah, it gets really small, approaching 0. Very small. So you can get the end behaviors that way. All right, so there it is. There's your new parent function. F of x equals e to the x. Let's just write in here, of course, e is approximately what, just so you all know? 2.7, maybe 1.8 would be good to tag on there if you have room in your hard drive. 2.718. It's an irrational number. So again, it doesn't really matter when you're drawing one function how steep you make it, but it is important if you were to sketch another function on the same graph. Like if I had you sketch y equals 5 to the x on the same coordinate grid as e to the x, would 5 to the x be steeper or less steep than e to the x? Steeper, right? We said this yesterday, that for growth functions, the bigger the base, the steeper the graph. So it goes to infinity faster on the right, and it goes to negative infinity fast, or 0 faster, sorry, on the left. And it's the opposite for decay functions. Now, the smaller the base, the steeper the graph. So if I were to sketch 5 to the x on there, they would still pass to the point 0, 1, but it would be a little bit steeper. So it goes to infinity faster, and then it would actually cross here and go to 0 faster. So again, that is the only time the relative steepness matters, is when you're sketching two compared to each other. All right, so would anything change in terms of 5 to the x that we wrote down? Would the domain change for 5 to the x? No. Would the range change? No. How about the y-intercept, the x-intercept, the monotonic increasing over its domain, the one-to-oneness, or the end behaviors? Would it change? No. It's going to be exactly the same for any function, really, that looks like that, as long as the base is greater than 1. And in this case, the y-intercept will change if we let a equal something other than 1. So when a is 1, then everything's the same. What about a decay function? If you looked at y equals 1/2 to the x. Let's choose burnt orange for that. If I graphed y equals 1/2 to the x, would that be growth or decay? It would be decay. Now, would it be steeper than e to the x or less steep? Remember, 1/2 to the x comes from 2 to the negative x. So 2 to the x would be less steep. So if you're drawing it, it's actually going to be a little bit flatter. It'll look like that. So y equals 1/2 to the x. It would still have a y-intercept of 0, 1. Would any of the information change now that we gathered for e to the x, if we're talking about y equals 1/2 to the x? Would it still have a domain of all real numbers? Would the range still be greater than 0? Yes. Do the end behaviors stay the same? No. They switch. Good. They switch. The y-intercept, is that still the same? Yep. X-intercept, still none? Still monotonic? But monotonic decreasing now. Good, good, good. Still 1-to-1. So the only thing that really changes is the fact that it's decreasing, which changes the end behavior. Sweet. All right, so now we're going to talk about transformations. And you had transformations pretty extensively covered in Algebra 2. Hopefully you remember everything. I used to spend a whole week reviewing it with y'all, but because Algebra 2's kind of stepped it up, I don't have to anymore. But I do want to go over it with you somewhat in a detailed manner. So we have the instructions to sketch f of x equals 3 minus e to the x minus 1. So whenever you're sketching something without a calculator, the first step is to, number 1, identify the parent function. And so you can refer to that, and you know then that it's going to be some modified version of that graph. What is the parent function here? Is it x squared? No, it's what? It's e to the x, right? It's not just 5 to the x, it's e to the x. You can kind of see it right in there. All right, so at least what you're doing is now you are giving yourself kind of a frame of reference. In your mind or out to the side somewhere, you're just imagining this right here. There's y equals e to the x. Yep. I don't know why I changed colors, but it's a nice blue. Okay, And so what we need to do then next is to systematically put our equation into what's called standard transformation form. Put the equation into standard transformation form. And I don't think y'all necessarily called it that in Algebra 2. When you studied quadratics, you probably called it vertex form. But here's what standard transformation form is. It's y equals a times f of b times x minus c, close, plus d. And we use capital letters to denote coefficients that affect the graph the exact same way regardless of what the equation is. As long as you know what the starting graph looks like, your A, B, C, and D will always affect that graph in the exact same way. So just to review, the A and the B are multiplied. And anything that's multiplied is going to be a dilation. It's a stretch or a compression. If A and B are negative, then they're also reflections. C and D are added or subtracted. So that's going to be your translations or your shifts, moving them left and right or up and down. Now, that's the first thing you have to understand. Is it multiplied or is it added? Multiplication will change the shape and maybe the orientation, reflection across the XY axis. The C and D are shifts. They don't change the shape. They just change the location. The other thing you want to understand is where they occur. Notice your A and your D occur outside the function. And anything that happens outside the function is going to affect the Y values, or it's going to affect the graph vertically. The B and the C, they occur inside. Oops. And anything that's happening on the inside is going to be affecting the graph's X values, or its horizontal information. If you understand those two things, then you understand everything. So here we go. Let's just list them very carefully. A is going to be your vertical dilation factor. It's either going to be a stretch or a compression. Stretch means you make it bigger. Compression makes it smaller. Now, if A is greater than 1, it's going to be a stretch by a factor of, which I'm going to write as BFO A. So if A were a 2, it's going to be a vertical stretch by a factor of 2. All your Y values are twice as big. If A falls between 0 and 1, like 1/2, it's going to be a compression, but now by a factor of not A, but 1 over A. So, in other words, if A were a 1/2, your graph is now half as tall. But when you describe it, you don't say it's half as tall. You say it's vertically compressed by a factor of what? The reciprocal of 1/2, which is 2. You've made it twice as small because it's now half as tall as it used to be. You've compressed it by a factor of 2. Let's go ahead and talk. Oh, and then one other thing. If A happens to be less than 0, let's take the absolute value of it right there. If A happens to be less than 0, then it's going to be an x-axis reflection. So it really does two things, possibly. All right, I'm running out of room here, so let's go to a new column. Going from left to right, which is nice, B is the next value. And it's also multiplied. So that's going to be your horizontal dilation factor. And again, it's going to be stretched or compressed. But this one's the opposite of what it appears. So in this case, if your absolute value of B is greater than 1, like if B were a 2, it's not going to make it twice as wide. It's going to be a horizontal compression by a factor of B. And if the absolute value of B is between 0 and 1, like 1/2, you might think it's going to be half as wide, but it's not. It would be twice as wide. So it's going to be a horizontal stretch by a factor of 1 over B. So anything on the inside, whether it's a B or a C, is going to be the opposite of what it appears. The other thing you need to do when you're listing what's happening is you never want to say by a factor of something and have it be less than 1. You always want to say by a factor of something greater than 1. So if your A or B value are less between 0 and 1, then always flip it. It's by a factor of the flip. So in this case, in other words, if B were 2/3, that would be a horizontal stretch by a factor of 3/2 or 1.5. It'd be 1.5 times wider. We'll practice that in the context of the problems. Okay, so one last thing. If B is less than 0, that is going to be a y-axis reflection. Y'all probably had less experience in Algebra 2 with B values because they can be a little bit tricky. But we're not afraid of them in here. All right, then the C and the D, those are going to be pretty easy. Your C and your D are added and subtracted. So this is your horizontal shift. And it's the opposite of what it appears. And y'all are pretty good at that. So if that were like an x minus 3, it'd be right 3. And then your D is outside, so that's going to be your vertical shift. And that's going to be exactly as what it appears. So if you have like +5, it's up 5. If you see -5, it's down 5. So those are a lot easier. So A, B, C, and D, if you do them from left to right, you're doing it in your dear Aunt Sally's preferred order, which is multiplication first and addition, subtraction second. Now, we do have AM assembly here, so we'll be in here until 10:30, and then they'll call the seniors to some assembly. All right, so now that we have all that, y'all have all that? Or at least, yeah, you got it up here, if not written down. Let's go ahead and kind of shrink that down to a space bag, or just put it in your head. I'm looking to shrink it down pretty far. It's still there if I need it. That's mighty tiny right there. Can we do it so much we don't even see it? We want to see it, right? There you go. So I can resize it larger if I need it. Okay. So now I know the parent function is e to the x. Is this in standard transformation form? No. The 3 in the front is being added on the ground floor, so that's your D value. So you would have to put it at the back. Now this is in standard transformation form. So let's talk about what these things do. The negative in front is going to be your x-axis reflection. And that's an important thing because it's going to change the orientation. But that's the only A or B we have, so everything else is going to be pretty easy then. Then you're going to pick up your graph and you're going to move it what one? Left or right? It's right one. It's opposite of what it appears when it's inside. To be inside means to be in the exponent for this function. And then the +3 means we're moving it up 3. All right, so let's do this one first by what's called a sequence of transformations. And then what I'm hoping is that you won't need to do the sequence part. You could just go straight to your final graph. All right, so I'm going to use a light color here, like yellow, to give my parent function. So there's y equals e to the x. It's very light. Now we go from left to right. So what does the negative in front do? Well, it takes that graph and reflects it across the x-axis. So now we're working with that. That's y equals negative e to the x. And now we're going to pick that graph up and move it what? Right 1 and up 3. Now the right 1, you can actually kind of grab that and just move it to the right a little bit. Notice that's not going to be a very interesting transformation, is it? That just slides it. It makes the y-intercept either a little bit closer to 0, or if we move it to the left, it makes it more negative. But it doesn't really change much about the graph other than the y-intercept. But the +3, is that a big one? Yeah. Why? What normally do we have at y equals 0? We had a horizontal asymptote, and when I move everything up 3 units, guess what happens to the horizontal asymptote? It moves up as well. So let's go ahead and do that. I'm just going to arbitrarily call that 3, and I'm going to put my horizontal asymptote first. Which anytime you're sketching a graph and you have an asymptote, whether it's horizontal, vertical, or slant, whatever, you want to draw it first because it's going to act like a guideline for the graph. It's like gravity. The graph is going to be irresistibly attracted to it. All right, so now what's the shape of my graph? Well, it's like the green graph down below. So because we have notability, I'm going to actually get rid of the yellow one so it doesn't obscure what we're doing. And I'm going to get rid of the name of the green one because we're actually going to move it up and now and to the right. So here we go. Grab your scissors. Let's move it right first. Right 1, there it is, and we move it up 3 right there. Boom. And now I'll just trace over it with my final color. And all I'm going to be interested in is, do you have the right shape of your graph? In this case, the shape is decreasing from left to right. And you have your horizontal asymptote in the right spot. Now, there's one last thing that you need to do, and it has it in the instructions, but let me talk to you about it before we read. I moved it right 1 unit. We don't have anything really marked other than the 3 on the vertical axis. Look what happens if I were to pick this graph up and move it right, if I continue to move it right. That's only going to make the y-intercept probably a little bit bigger. But what happens if I move it left? If I keep moving it left, what happens to the y-intercept? It becomes negative. So the horizontal shift, as you'll see a couple of examples or tomorrow, the horizontal shift is also going to be the same as some kind of vertical dilation, which means it changes the y-intercept. So in order to make sure that you have it crossing the y-axis in the right location, either positive y-land or negative y-land, you're going to always have to find the y-intercept. And that's a real easy thing to find. Now, for the y-intercept, it makes sense to go back to the original version that was given to you. Standard transformation form would also work, but it's a little bit nicer for graphing. The original form is probably easier for evaluating. So you show me that you're finding the y-intercept by writing what? F of 0. And I'm like, hey, they're going to plug in a 0 for x. And here we go. Let me move it down below the intercept. Okay, so we got 3 minus e to the 0 minus 1. Now, there's your exact answer. But that doesn't really tell us much about where it crosses. So let's simplify that. That's 3 minus e to the negative first. Now, e to the negative first is the same as about what? What's another way to write e to the negative first? 1 over e to the positive first. Now, if e is about 3, then 1 over e is about a third, right? So what would 3 minus a third be? Positive or negative? Positive. And that's all you need to know for that graph. So there would be the exact answer for the y-intercept, and it's positive. So is my graph crossing in positive y-land? Yes. So we have it drawn correctly. And if you want, you could actually label that as 0, comma, what do we write? 3 minus 1 over e. A calculator would tell you what that is. But it is less than 3, obviously, which we have it below our horizontal asymptote. So let's go ahead and talk about just a couple of things here. What's the domain of that new function? All real numbers. Is that ever going to change even if we transform things? No. Move it left, right, up, down, flip it, stretch it. It's still going to be all real numbers. But the range is a more interesting question. What's the range? Three to negative infinity? Is that the right way to write 3 to negative infinity? No, interval notation always has to be from least to greatest, so that would be wrong. You would have to put negative infinity up to 3. Yeah. Or say the set of all y's such that y is less than 3. Either one. Now, that makes a great multiple choice question. Do you have to go through the process of sketching the entire graph to come up with that answer? If you know that an exponential function's range is always going to be either entirely above or below its horizontal asymptote, you can answer it pretty quickly. Ours lives below the horizontal asymptote. What made it live below the horizontal asymptote? The negative out in front. Yeah. So if you see a negative out in front, it's going to live below the horizontal asymptote. If there's a positive out in front for your A value, it's still going to live above the horizontal asymptote. So that'll tell you y is less than or y is greater than. Now, in this case, our horizontal asymptote was at 3. How did we move it up to 3 from 0? It was the plus 3 in the equation, right? So, in fact, for exponential functions, if you want to, well, I already shrunk it way down, but the d value, you're going to have your horizontal asymptote at y equals d. Pretty sweet. And then all you have to do is know if it lives above or below that to get your range. So you don't have to graph it to answer the question about the range. All right. Questions on that one? Oh, what's the end behavior? What would be the limit as x goes to infinity? It would go to negative infinity. And the limit as x goes to negative infinity is what? 3. Yeah. Do you have to sketch that graph to answer those questions? Or is there a way to get those answers without grafting it? Well, let's see. If I come up here and again I quote-unquote plug in a positive infinity, I get 3 minus e to the infinity minus 1. What's infinity minus 1? It's infinity, right? And what's e to the infinity? Huge number, right? So what would be 3 minus huge number? Negative huge, right? That would equal negative huge. Is that what we got? Is our end behavior? Yes, negative infinity. So you could actually plug it in. You could do the same thing for the other direction. F of negative infinity, quote unquote, would be 3 minus e to the, what's negative infinity minus 1? Negative infinity. Yeah, you owe me a gazillion dollars and then you owe me one more dollar. You still owe me like a gazillion dollars. And that's the same as 3 minus 1 over e to the infinity. What happens to 1 over e to the infinity? 1 over e to the infinity goes to 0, doesn't it? And so we get 3 minus 0, which is 3. So that's kind of cool with infinity. You can kind of plug it in and just kind of see what happens. All right, let's go to example 7. Same exact instructions, but now we have a different equation. What's step 1? Panic? Oh, nope. We need to identify the parent function, the mother function, if you will. What is the mother function? Is it e to the x? Is it x squared? It's not e to the x, it's 7 to the x. Right? The base is 7. And what would 7 to the x look like? Wouldn't it look a whole heck of a lot like e to the x? Just a little bit, what, steeper or less steeper? Steeper, yeah. Less steep, not less steeper. So, kind of the same idea. All right, next question. Is that in standard transformation form? No. So let's go ahead and put it into standard transformation form. The 4 that's being added in the front is your d value, so it goes to the back. So we get negative 3 times 7 to some power, and then we get plus 4. We already know that we have a horizontal asymptote at 4, don't we? Let's just answer the range question before we go anywhere and see if it ends up being correct. The range of this function should be the set of all y such that y is either less than 4 or greater than 4. Which one? What does the negative in front do? Reflects it across the x-axis, which was originally where the horizontal asymptote was. So just like the previous one, it lives below the horizontal asymptote. If that had just been a positive 3, it would stretch it vertically by a factor of 3, but leave it above, and then it would be y is greater than. So that's all you really need to do to answer that question. We'll verify. Now, if there's work to be done to put it into standard transformation form, it's going to be inside the function. Let me go ahead and rewrite it here without all the extra stuff. Because inside, in order to get your shift right, your coefficient of the b has to be a 1. If there's a horizontal shift, you have to factor out whatever the coefficient of x is from both terms on the inside to get your horizontal shift correct. And the x term has to go first. So let's go ahead and do that. I have a 5 minus x. So at first, I'm going to write that as negative x plus 5. Now, if you left it like that, you might say, the negative in front of the x is going to make the x value switch places, which would be a reflection across the what axis? The y-axis. And then you're like, the plus 5 is going to move my graph to the what 5? You would say to the left, right? Because it's opposite of what it appears. But that would be wrong, okay? And the reason is the coefficient of x right now is a negative. So if there's work to be done, it has to be done on the inside of the function. Here's what you need to do. Negative 3 times 7, and on the inside, we'll factor out that negative from both terms. And now it becomes x minus 5, and then plus 4. Hey, no problem. And so now it is still a y-axis reflection, but it's really shifting the graph which direction? Left or right 5? Right 5. So if there's work to be done on getting it in the standard transformation form, it's going to be the inside part. The coefficient, if there is a shift, has to be a 1 on the x in order to get the shift correct. Okay, so let's go ahead and sketch the final graph without having to do all the sequence. We'll just draw it like that. Well, no, I'll show it here. Our parent function was growth. The 3 is just going to make it a little bit steeper. So it looks like that. What's nice about this function is you can go from left to right. Now, I can either stretch it by a factor of 3 and get the top graph, or I could reflect it across the what axis first? The x-axis. It doesn't really matter. It's the same priority level. I'm going to go ahead and erase them as I go. So I started with the bottom one, and when I stretched it by a factor of 3, I got that one. It's a little bit steeper. You don't really have to show that. And now I'll reflect that across the x-axis, and now it looks like that. So here's my current shape just from the negative 3. Want to agree? And if you look at that, you're going to tell me, hey, that looks like about 3 times steeper than the original. And I'm going to go, thank you. And that's the same standard I'm going to hold you to. The negative is actually more important. Now, keep going from left to right. What does the negative in front of the x do to this graph? Flips it across the y-axis. So now it's going to make it look like this. And now I can get rid of that. So notice I flipped it twice, x-axis and y-axis. So now it's back to a growth function, but it's living below. Now moving it right 5, I'm not going to really show that. But it's going to look like this. Ready? Right 5. There it is. But what's the actually more important shift? The up 4. So now I'm going to go to my final graph. I'm just going to mark that as 4. And just shift it up. And I'll just draw a new graph. What the heck? It looks like that. All right, perfect. Now, did we get our range right? Is it less than 4? Yeah. Hey, should we walk away and feel victorious? No. I moved this graph right 5. Notice my y-intercept right now is currently positive, yes? If I move it right 5, that's kind of a big number. It could be that I moved it right enough to make the y-intercept do what? Become negative. So notice if you shift it left or right, it's only going to change your y-intercept. So rather than have to worry about how much we're actually shifting it horizontally, because it's really hard to show that, guess what you're going to do instead? You're just going to find the y-intercept. That's all you have to do. So let me just kind of set that guy back down, and I'll come off to the side here and say, all right, let's find f of 0. And again, for evaluating the y-intercept, it's probably easier just to plug it into the original function rather than the standard transformation form. So you get 4 minus 3 times 7 to the 5 minus 0 power is to the 5th power. Now, let's just think about if that number is positive or negative. 7 to the 5th, big or small? Huge, right? Times 3, huger. So what would 4 minus a number bigger than 4 be? Positive or negative? Negative. So it's just going to be less than 0. It's negative. That's all you need to know. Here's the exact value of the y-intercept, and it's negative. So look at your graph. Is mine drawn correctly? No. And if yours is looking like this, it's not correct either. You need to redraw it, or on Notability, you can just slide it to the right enough so that it has a negative y-intercept. And that's all I'm going to be holding you to. Does it cross in the correct spot? Now notice, if that is a 4 up there, this looks like it's actually like negative 1. I'm not going to care if it's the right numeric value or not. I'm going to care if it is in the right location, positive or negative. So that right there was senior assembly.
At this time, all seniors need to report to the auditorium. That's just seniors will report to the auditorium.
All right, I'm going to work a bonus example. So if you're going to the assembly in the auditorium, you can check out the shared folder. There'll be one more bonus example, and then we'll call it a day. All right, so give me 5 more minutes. What would be the limit as x goes to infinity? Let's answer that before we move on. 4, and the limit as x goes to negative infinity would be negative infinity, okay? And we got our range spot on. All right, so here's the bonus example. Let me add a page, click, add a page. All right. So you saw this coming in, Rylan. You thought we were giving away extra points today. We're just giving away extra problems. Bonus problem. Giving you extra problems, right, as if you didn't have enough. Man, how to get a girl. Different problem. Hey, at least we all love to write today. Here's your bonus problem. I want you to graph the function y equals 2 times 0.7 to the 3 minus x power minus 5. Okay. Now let me start you off or help you out. What is the parent function? Yeah, it's 0.7 to the x power. So I'll use kind of that aqua velva blue there. Very wintry fresh. And that's going to be a what function? Growth or decay? 0.7 is what? Greater than 1 or between 0 and 1? Between. So it should be a decay function. So we're starting off with the decay function. Good. Let's answer the range question very, very quickly. Very, very quickly. The range of this function should be, well, it's minus 5 for the d value, right? So it should be the set of y such that y is something, something, negative 5. Is it going to be below negative 5 or above a negative 5? Do we ever reflect it across the x-axis? No, because it's a positive 2 in the front. We just stretch it vertically by a factor of 2, which makes it look a little bit more like that. So it should be y is greater than. So the range is easy to find now. Notice that the inside of your function is not in ready-to-go format. So what you're going to have to do is write that as 2 times 0.7. Put your negative x plus 3 first, and then on the next step, what are you going to do? Factor out the negative. Now, it doesn't have to just be a negative. It could have been like a 2x, and we'll see that later on. Then you would factor out a 2 from both of them. And in this case, you factor out the negative, and notice it changes the sign. And I had the minus 5 in the back to begin with. So is this in standard transformation form now? You have your a in the front. Let's say what it's going to do. The 2 is going to be a vertical stretch by a factor of 2. You don't really have to show that. The negative in front of the x is substantial. That's going to be a reflection across the y-axis. Good. Just think your x's are now opposite. Then it's going to pick the graph up and move it right 3, which again we don't have to show because we're going to find our y-intercept. And then we'll move it down 5, which is very important because that's the horizontal asymptote. So go ahead and sketch the graph and find the y-intercept. I'll give you like 2 minutes, a minute to do that. Y'all can do that fast. And then we'll be done for the day. But not forever. Thank goodness. Man, I love to write today. Anyone like lemon heads? Candy? How many lemon heads do you like? I have 3. 2.5? All right, let me get going on this one. I'll give you what's left. Jaw busters? Anyone? Jaw busters? We're almost done with all leftover Halloween candy. How about a Tootsie Roll bubble gum? Nope. Regular bubble gum. I don't know. Just ignore them. All right, so here's how we would do this, and hopefully you're done. Got the y-axis, you got yourself an x-axis. Here's what I'm going to put first. Even though it's the last thing we do in the sequence of transformations, I'm going to go ahead and put my negative 5 down there first. I know that's the horizontal asymptote. And I know the graph lives above because there is no negative a value. So I just need to work on my shape. So I know that then it started as decay, I stretched it, and now when I flip it across the y-axis, it's actually going to be like that. So my final shape is an increasing function above the asymptote, correct? And that's all you really need to consider when you draw it, for the most part. It's going to look something like that and like that. Now, what's the only thing that we need to be very, very careful about? The y-intercept, because if I pick that up and I move it left or right, if I move it to the left, it becomes positive. If I move it to the right, now it's 0, and if I keep moving it to the right, it's negative. And I moved my graph to the right from where it used to be, so there's a good chance it's probably going to be a negative number, but you never know until you plug it in. So let's go ahead and find it. And we get y of 0, and it's 2 times 0.7 to the 3 minus 0 power is 3 minus 5. Now, 0.7 to the third power, you don't need to really know what it is. Just know, is it going to be small or bigger than 0.7? It's a lot smaller. 0.7 squared is 0.49, right? And then times another 0.7, it's going to make it like 0.2 something. So it makes it really, really small. If you raise a number between 0 and 1 to a larger power, it makes it smaller. So 2 times a small number is going to make 2 even smaller. So something that's smaller than 2 minus 5 is going to be what? Positive or negative? Negative. And that's all you need to do. Don't even put equal signs there. Just go at the back and put, hey, that's less than 0. So I know it's going to cross in negative land. Does my graph cross in negative land? Yes, it do. It sure do. And if you had it drawn incorrectly, if you had it drawn like this and you walked away, then you're going to lose points. But as long as you have it crossing in negative land, even if it's like that, I'm going to be like, yeah, way to go. Plus, I'll also see this right here. The inequality is very important when you find your y-intercept. Less than 0, greater than 0. Yes? Yeah. No. It would actually, the horizontal asymptote would be at -5. Because where does it always start to begin with? At y equals 0. And if you stretch or compress or flip, it doesn't affect 0 at all. The only thing that affects the horizontal asymptote, the only transformation, is your vertical shift. That's the only thing. So if it starts at 0, it's down at -5. Now what you're thinking of is the original function had a y-intercept of 1, which was 1 unit above the horizontal asymptote. So if you were just to shift that down 5, now it would be at -4. But we've stretched it and compressed it, so that's why we just find the new y-intercept by plugging in. You don't have to follow, in other words, you don't have to follow around any points on the graph of any of the exponentials, like you would do the vertex for x squared. You just get the general shape. Does it live above or below? Is it increasing or decreasing? And then find the y-intercept and make sure it crosses in the right location. It's that easy. It's so easy, it's almost fun. In fact, it's fun easy. It's fun easy. All right, we're done for the day. Any questions? Tomorrow we'll pick up right there. Would y'all want a quiz tomorrow? Would y'all be desiring that? How about Thursday? We'll quiz on Thursday. Yeah. All right. Well, we're just going to hang out for a while until the senior assembly.